right, guys, we'll go ahead and get started. Second part of electrical controls or electrical fundamentals or whatever we want to call it, just the basic fundamentals of electricity. And we'll go over motors tonight and go over just a few different things, motors and wiring, kind of where we left off last week. I know we talked about or drew a little diagram on the board. We're going to wire that up. We're going to check the voltages and stuff and see exactly how what the voltages do, what the amperes do, or whatever we want to call it, however we want to go about it. But the very first thing I want to do is I want to figure out where we're at, where each and everyone's at electrically. So who would consider themselves strong electrically? Nobody?
No risk takers.
All right. McKinley, did you draw a refrigeration diagram?
No, sir.
Yeah, you can. So, with that said, well, let me ask this question one more time. I want serious answers. Who could draw a simple refrigeration electrical diagram? All right. So, if you can't, raise your hand. Three.
Greg's fingers.
So, what I want you to do is, if you can't, that's fine. That's what we're here for. No problem. Don't be embarrassed. Don't be ashamed. Chris will make fun of you, but just don't pay attention to him. What I want you to do is, I want everyone to draw a simple electrical diagram for a refrigeration unit. So, just say a split system. We want to draw a electrical diagram for a split system. That includes what components? Compressor what?
Compressor contactor.
Compressor contactor is one. What else? Condenser fan. Capacitor.
Lower motor,
Capacitor.
lower motor contactor,
Lower motor contactor. Thermostat. And I want those couple safeties in there. High pressure, low pressure, and fan cycle switch. So give you 10, 15 minutes, draw it out. Like I said, if you need help, don't worry about it. That's what the class is for. If you can't do it, don't worry about it. But I want you to give it your best shot. I'll write these on the board so everybody knows.
Do I need a mechanical pencil?
Yeah.
Nice.
I don't around all this shapes and crap wrong.
And I don't know if we mentioned it, but thermostat as well. So you don't have to draw a thermostat out like you typically say, just use a contact or whatever, if that makes sense.
Yeah.
IB means indoor blower contactors. You Oklahoma City guys hear what I said? I don't know if you can see this, what I wrote down or not.
Yeah, we got it.
All right. Once you guys get these drawn out, we're gonna come up here, we're gonna wire it up. According to your diagram.
I can't draw that.
And when you get Oklahoma City guys are done, just text me your drawing, if you don't mind. Everyone need, what,
You said just high pressure and low pressure?
hand cycles. I didn't even clarify, but what I said, I'm assuming everybody's just drawing the control voltage circuit.
Oh, no.
If you're drawing a high voltage circuit too, that's fine. That's fine. If you drew the high voltage circuit, that's even better. Yep.
So, never mind. So. I drew some of those components on the high voltage side.
We'll look at it. Couple more minutes. All right, time's up. Everybody pretty much get it done or close? Not done? Okay. Did anybody get it done? Anybody confident in it? Nobody? Kinley? You talking all that smack?
Man, I was drawing the whole thing. I was doing high voltage.
Did you heat too? Put the heat in?
No, no heat.
Did anybody know? So nobody feels comfortable.
Comfortable in my outdoor unit. I ain't doing my indoor.
Feel comfortable, Chet? Did you draw it out, Chris?
Sure.
All right, come on up here. So everybody kind of come stand around. Let's see your diagram real quick.
I went back.
You went
Yeah.
backwards, basically.
Yeah, so this is high voltage. So there's my control circuit, and I just crammed a bunch of stuff in. So there's my thermostat. And cycle switch, high pressure, low pressure. in
Okay.
Series with the contacts.
I didn't write these out, so I should have. Draw this up. I think they're all wet markers.
No, I just seen something wrong. No, I'm not confident.
All right, let's let Chris King do it. Show us how to do it. And we'll draw it up so everybody has it. So Chris, you're gonna wire this up for us.
Okay.
So we want to draw it out. So let's say this is the compressor contactor. I don't know if Marshall wanted, he didn't label anything, so I don't know if he wanted this or not. Condenser fan contactor, indoor blower. And we'll make these the low. I guess we can do low. This is the 120 in case nobody knows. This, I'm sorry, 120, should be 120 to the transformer, and this is 24 out of the transformer. Make sense? And these are just all switches. So if we were gonna do this, basically, we ohm across that, we know that. So if I ohm across this right now, what should I get across those 2 points? If I go here to here, what should I get? Tell me.
If it's on,
All right. So what does that mean?
So
Close.
Continuity, so that means it's closed, right? Everybody understand that? So, closed, I'm gonna read what's my meter gonna read? Continuity, but what's it gonna read?
Should it be 0 ohms or?
0 ohms, close to 0, right? So that means I get a direct path, basically saying, just like me touching my leads together. Right now, my leads together is reading 1.3. So if I go here to here, read 1.5, so basically the same. So open it up, nothing. So what's it mean when my meter says OL? Open load, over limit. What does that mean though? Tell me what it means. Infinity resistance, right? That means there's between these 2 points or whatever I'm touching, that means there's no path, there's nothing, it's infinity. So that's all it means. So I read OL, it means there is infinity resistance. So same thing, you go across these things. So here, these two right here is going across the load of the bulb. I'm reading 25.9, 25.9. So that tells me what? Bulb's good, exactly. That there's a path between these 2 points going through that bulb. You're going through that element, right? So just like we talked about Ohm's law last week, we could do the Ohm's law and figure out what the amperage should be on this, right? I know what? Voltage and resistance, exactly. So we can get that. So if I want to get amperage, what I need? There we go. So if I want current, amps, I just basically take volts divided by resistance. So again, compressor contactor, pretty simple. These are just a bunch of different switches we're going to use. So let's say this is Y. I'll make this, let's make this G here. Just because I like to go left to right. I'm just anal about this stuff. So Y, G. Is there anything else we need for the thermostat in this circuit?
R.
R? Where's R going to be? R could be right over here.
R and C could be there.
Or we can put it there. I mean, however you want to say it. So we can just say this is R, C. Is there anything else that we need to label? What other switches do we have? Low pressure. So we got low right there. High pressure. And we can make one of these fan cycle. Make that one fan cycle. So this one's got 3 points. So what does that tell me? So if we don't know, what can we do? We just ohm this sucker out. So right now, the switch is in the bottom position. So what does that mean I got between these 2 points? Read 1.2 amp or 1.2 amp, 1.2 ohms. So that means that switch in the down position, I got a path. So if I go here, what does that mean? Infinity resistance, right? So now let's take the switch up. Infinity resistance. Infinity resistance. What does that mean? We got a path there. So I don't know how that switch is wired, to be honest with you. But all I do know is if I go here to here with that switch in the up position, in the down position, I got a path. So we can use that switch, just have to ohm those out to determine how we want it to operate.
Top left is your common. Yeah, so how are you gonna figure that out? You got everything you need right there to figure it out. How you gonna figure it out? Anybody?
Moment. Show us how to do it.
How to figure out which one's common?
Yeah. Oh. And then you can write it down.
So. So you figure out which one goes between, and when you go to the other one, you figure out, okay, so that was the one that was consistent between them, right? So this is the only one you're moving, so that's the common one. Make sense?
So write it down there if you don't mind. Just put the comment on the terminal. Yeah. Yeah. So this is, I mean, this is good because this is like, if you go to a unit and people, and it's an older unit, people made wiring changes, this is stuff you're gonna have to do. You're gonna have to figure out how it's wired, because it may not be wired directly or according to the wiring diagram. Hopefully it is, but sometimes they're not. Chris talked about the other day, we were talking, it's totally different type of equipment, but it's kind of the same thing. I retrofitted a RTAA chiller with the MCS, and there's no wiring diagram on that thing. And he said he saw that for the first time, was cussing me because there's no wiring diagram on it. But if you know electricity, if you know how electrical circuits work, if you know have a basic foundation, you don't need a wiring diagram on those things. They're that simple. So once you have a good foundation, like we're talking about here, you can do a lot of things without a wiring diagram. So
It's on the screen. So even though there was no diagram, but you're thinking like, what's hooked to M1 or M7 or whatever. If you look on the screen for it, the Magnum controller, it tells you
exactly.
M1 low pressure switch or whatever. So it's like, it doesn't make any sense. And I got to looking at the screen, I'm like, oh shit, it's all built into it.
All right, Chris, show us what you got.
I'm
man.
gonna do this, but you guys are gonna help me, so I know how to do it. So what needs to happen to bring the compressor on? What we gotta do?
Control voltage.
What turns the compressor on? Thermostat, right? So what's R on thermostat? What terminal thermostat we need to turn the compressor on? What has to be, what, if there's an issue, what needs to turn the compressor off? If there's a safety problem. Pressure and what we got on pressure. High pressure, low pressure, right? So we're gonna come off of R. It's actually R2. Okay, so now we got power to the thermostat, which I'm on.
Hang on, let me draw this up while you're doing that too, so we can put on the wall.
Each guy's texting Dylan about that.
I did.
I'll just say years.
We can zoom that camera in on that.
Yeah, that'd be great.
Yeah. Probably better if we just stop sharing that. So we're not just looking.
I'll stop sharing that. I wouldn't share it anyways.
All right, good. Got it. Okay, so we're gonna go off of Y. That's got to turn the contactor on, but low pressure and high pressure need to be able to turn that off. So we need to wire those in parallel to the compressor contactor or series.
All right, so let me go here. So we're at R, then when you went to what?
Y.
No, you're drawing. So if you come,
I don't need that R right there for one thing.
So this. I'll take it off for now. This wire right here, up there, what's wired? So this wire, next one. So where's it gonna go? It needs to go in series with. Come out of the low pressure switch, high pressure, right?
Yep.
Doesn't matter which one's first. No matter. Now the high pressure, now what are we gonna go to? Pressure contact.
All right.
Now the other side of the coil, where'd you go to? That line, right? So that's one complete circuit. Just wire the compressor. We'll need to turn on condenser fan. How we gonna get that on? Or let's do the blower first. How we gonna get the blower on?
You want to come on when you enter the water?
What? Fan, the indoor fan?
No, come on.
Fan goes off the G.
I didn't draw that.
Those are fans. The fan does come on with G off, so anytime Y comes on, the fan comes on as well. So we can do both.
Option conserving energy.
I should draw that. He's making a Yugo out
He's
of
got
it.
an attic
He's
fan
making
in
it
his
simple.
house.
Yeah, that's a good point. So why do we wire it to G? If
So you can
If
run
it
it
comes
fan
on.
on.
So now, we got any safeties for the blower motor? Just running that back straight.
So from G, where we go? Blower motor, that's the blower motor?
Is that contact? All right, now we gotta do condenser fan, right? So where's the condenser fan gonna come off of? Why? We gotta do to bring the, what else is related to this? What's the fan cycle switch do?
Pressure. So you could just run it, instead of running off Y, you could just run it straight to power. Right, straight to R, because you don't have the pressure, it should come on.
So how do we do that? How did you wire it?
We came off of R.
Came off the R? Do what?
No, I came off of Y.
Came off of Y.
Came off of Y. Went to fan cycle.
Yeah.
Maybe, I don't know. So out the fan cycle, we go to what? Condenser fan.
Yeah, control side's done, right? Now we go wire motors up.
So did everybody draw it like this? What did you miss?
Whole control side, because I drew the other side first.
Probably schematics. They're open, so close.
Toast.
So schematic should be drawn in the de-energized position. So.
Is this de-energized or energized?
No, it ain't mine.
Energized.
Yeah, I think the switch should be closed.
So just like we talked about, this is the stuff that we have to know off the top of our head. This is as simple as it gets. So this is something that we need to know, and so it's something that you just need to practice when you're out on a job. Just think about what's going on. So it's like the compressor contactor. What will shut off the compressor contactor? I mean, and again, I'm just asking a rhetorical question, but what energizes it? What shuts it off? Blower motor. What brings it on? What shuts it off? Condenser fan motor. What brings it on? What shuts it off? So the condenser fan motor is coming off of Y, but where else could we put it in there? Where else could that condenser fan motor be brought on? So right now, if this compressor goes out, if it opens up on either of those switches, which are open right now, does that condenser fan motor still run? Still runs, right? Do we need it to run? So where else could we put it at? Where else could we bring power for that at? We can go right here, right? So now if the compressor is not running, this fan's not running. So those are, like I said, those are just the simple things that you can think about and just do, because if you can get this, understand these things, you can understand the bigger equipment. But you have to be able to understand this stuff right here. So it's pretty simple diagram drawing. So just what Josh said earlier too, because I think I look at it the way Josh did, because I don't really think of the fan coming on G, because it can. You turn this thermostat to fan on. That's what you're doing. You're closing this. So say the thermostat is in auto. How does that fan come on? Because right now, the way it's drawn, just the simplicity of it, it's not going to come on. Wire W. So which would be, I can come off right here, right? Right off the Y to the fan. That way the fan comes on. So if I were to draw a line right here, is there any problem with that? So say this is closed. And somebody closes this.
That'll turn your,
So now it's going to bring the fan on, and say these are all closed as well.
that'll turn your pressure back on.
Turn the fan on, you turn it.
So there is a problem with that, right? Where do we put it? On the side of the compressor? What do you mean? So a thermostat isn't wired like this or whatever, so it's kind of hard to draw it right here, but you can't do that. Because of exactly what you said. You turn the G on, now the compressor's going to be running. So will the compressor ever shut off? As long as G's on, it's not ever going to shut off unless one of these opens up. So if you got the thermostat set to 68 and it's 67, that compressor's still going to run because somebody wired it wrong. So just little things like that. Just got to be able to read wiring diagrams, look at how a circuit works and operates. So, any questions on that? None?
Is it on the test?
All right, Chris, we can get it.
I did the hard part. I was gonna wire the other stuff up.
Wire the high voltage stuff up.
You didn't have wires.
We get up here, it's all right, it's down on this side. Didn't leave myself much room. Where are we going?
So we're going from, power to our compressor contactor.
Going to an open contact on the pressure contactor?
And then going to our, going to our compressor.
Can you tell which one was the compressor?
Their capacitor.
You paint that one black.
So, who drew this up? I'm assuming everybody drew the single phase. All right, so how do I draw that out? Draw it.
We don't have a capacitor on here, so, but
Draw it out with the capacitor anyways, if you can. Yeah. No, not much better. Yep. Which one of those is run, which one of those is start? Why is that start?
Start, it has a line. So your run is a cross line, and your start is in series with the capacitor.
Exactly. So anytime you see a capacitor in there, you know the start winding is which one? The one in series with the capacitor, right? So it's going motor basics, motor 101, which one has the higher resistance? Start. So we would see a higher resistance in the start winding. So if I went here to here with my own meters, I would get, let's just say, throw a number out there, say 10. 10 ohms. So here to here, I get 10 ohms. Then I check the other side, go here to here, and I get 6. So that means I know that's the start, that's the run, and we'll do that here in a second. So you can identify which one by these 3 leads. We'll ohm them out. We'll be able to identify which one's start, which one's run. So let's say you throw a hard start kit on there. You do that. So that's just a regular run capacitor.
It's another capacitor, sure.
Exactly. But what else does it have?
A potential relay.
Potential relay, something to take it out.
Open, yeah.
Exactly. So you could draw it right here and just draw it parallel, but you'd have to have just draw an open contact or something. Does that make sense? Everybody shaking their head like, yeah, you sure?
Dale Dillon said, ask Dale if a single phase blower can run backwards. Ask him to hurry.
No. Dylan proved me wrong. Well, he can make it run backwards either direction.
Comment on the- I thought that there was a comment on the capacitor.
Yeah. I argued with Dylan for like 2 hours straight, and he went home and he did it. So I still think he jacked something up, yeah. But yeah, I mean, exactly what he drew here. Good. And so, just like you said here, this open contact is basically a potentiometer. So that's what takes to start winding out once the motor gets up to what? 75% of its speed. So just like you put a hard start kit on a compressor or whatever, all you see is just basically the capacitor. You don't have to worry about, I won't say designing, but selecting a potentiometer or whatever. So pretty simple. So that's all that is, just to help it start and get it more boost to start. All right, keep on going, Josh.
Ran out wires.
Well, let's see if it works.
So my fan's not gonna come on.
Well, you ain't got. Dang it, we need more power. You got to power up the.
Someone I'll get more wires earlier.
Go grab them.
Got somebody who knows.
Hang on, don't turn it on yet. Unless you gotta put. This is the 120 right here.
What is this?
Unless you. Where'd you go from?
Let me see, that's 120.
That's 120 on for the power of the transformer.
Oh. I need to go up here.
So you need to go from here to here somehow.
Guess we're gonna find out.
Yeah.
You know that Kevin Chair was over here rewiring this before class.
Yeah, so once you plug it in, go ahead and plug it in, then we can see if we got 120 there.
Zip tie. You got a knife on you? Right, exactly, get it
Fix a
done.
lot of units with that.
Right. Get it plugged in? Plug it in. Boom. So we do have 120. So now you gotta put it down to the transformer. So the transformer ain't wired up. I didn't think it was.
Gun causes not.
Might as well go ahead and wire everything else up too, since you already have jumper wires. So what else do we have? Yeah, the fan socket switch.
Let's make sure what nothing touches.
Right.
I'm just throwing that.
Go with the same thing here, basically the same motor, right? So, condenser fan motor, what would it have? Kind of starting components or run components or whatever.
Just, run faster.
Just a running capacitor. Is that right? So same type of motor. Do you ever see a starting capacitor on a condenser fan motor? Yes, no?
Can you or have you?
Have you ever seen one on there? Never seen a start capacitor on a condenser fan motor. So if you guys,
Why do you think that is?
Because it's not starting under load, it's just,
It's easy to start, right? So that's what starter capacitor's for, right? Starting.
so why, when you say that, it's a good point too. Why do you say, or why is a compressor, you let it equalize before, let's say thermostat. Thermostat has a 5-minute time delay. Why?
short cycling compressor.
That's part of the reason. Load build up.
We just did the answer.
So if I were to shut a compressor off and immediately try to start it, what's my refrigerant pressures at? Already loaded up. My suction pressure is what? Lower. My discharge pressure is what? So that means my compressor is trying to start at a differential pressure. So that means it's going to take more starting torque or whatever to overcome that differential pressure. So if I let it sit for 5 minutes, what do my pressures do? They equalize. So now they're sitting at, say, 100 and 100. So now it's way easier to start when my pressures are equalized. So that's another reason why that's another reason why you have a time delay on your thermostat.
Josh.
Probably whoever wired that low voltage in. Shorted your, shorted what you do.
It's not working?
No, it worked, but it didn't hear.
It worked for a second.
Hold on, I'm thinking.
What's the matter?
We're just gonna turn the wire on? Yeah. Oh, never mind, hold on. Hold on. Oh, that's
You have one of these in school?
Oh, you didn't try that. That's what we're saying. All kinds you do. Chatter circuits, shunt circuits, everything that school was. He'll just check around the class, did something, wireless shit. Gosh, sputters at the school with the voltage.
Hold on, I'm wiring, Pete.
So when you see all these wires like this, man, it's hard to do. How many's been in a panel that look like that?
Oh my God. Carrier on top of Kelco.
Sorry, I didn't have my zip ties with me, clean the bit.
So that's a good point. So if you ever wire up a panel and you leave it like that, you should be shot. On site. Ain't that right, Jared? Amen. So don't ever do that. Wire it up, you zip tie it up, you make it nice and neat. That way you can troubleshoot, and that way you're not fumbling around with wires all day long.
What?
Didn't color coordinated, so.
So or you hit R, right? Or Y.
Water's on.
Are your
low
safeties
pressure.
There you go. So hang on, let's go back. Well, let's go back to that. So that's open. How are we gonna find that? Low pressure switch is open. How are we gonna know? How are we gonna troubleshoot to find that low pressure switch is open?
Start where you have power and keep going to lose it.
Show us.
Lick your finger, touch it.
It sounded so simple.
So where are you gonna start? Just look, we're at the diagram. We're looking at the diagram now on the panel. So where are we gonna start?
Right, power.
So we know what's not working. Compression not working. So we know where to start. This circuit right here, right? So where we're gonna put our lead?
You gotta call it Y.
So we're gonna go, where we're gonna put our leads at? Here?
R to Y.
Or the other side.
So we're gonna go here to here first. Let's do it.
Also, you know your thing's really loose, right?
Yeah. So if we go here to here, we're doing this with power on. All right, so doing this with power on. If I go here to here, what do you expect to see? 0? Because this is closed, right?
Yep. Or
Does everybody understand that? I'm gonna make sure everybody gets this. Why would we expect to get 0 across that contact?
No, I'm just.
No difference.
No potential difference across that contact.
No potential difference. So we got it. Voltmeter works off the difference of potential or potential difference. There's none right here. That's basically like having a wire going through there. So what do we get when we go across there?
So you go across the Y, or across that
The switch there.
switch.
I got the wrong deal.
Well, you just died.
Yeah.
Yeah,
It turned off on that.
likely you got a fluke. I seen a safety video.
Now you owe me $400.
This is your meter, isn't it? It's got copper in it. Yeah.
So you got 0. Now where do we go? We're still going to keep our lead right here. One lead right here. Where we take our next lead.
Low pressure.
We're going to go to here or here. This
Right,
one.
right side for you.
So we're going to put our lead right here now.
That's wrong side. That's right, yeah. Potential difference of 26 volts. Right now.
So you got, what'd you get?
Potential difference of 26 volts.
So you got 26 volts here to here. So we already went here to here, so we know that contact's good, right? So we go here to here, so now we know that that's open. So now we could fix the problem or whatever. So we fixed it, turn the switch on, act like we fixed it.
Jump wire.
Yeah.
Jump wire on it.
Right. Exactly.
Wire nut?
Now the compressor's running. So what else? We still got a couple others that's not running. Our fan ain't running yet. So we got.
Your side. The contactor pulled in, Jack.
This one did. So which one's a condenser fan? This one's labeled a condenser fan. This one, it's pulled in right now. It's not running.
Is that on?
Blew the light bulb
Oh, it did.
when you wired that line to neutral across the line.
Home it out. You can't just take it out. You ain't changing parts.
Parts changer. He thought it was a heating.
Yeah, that's so.
There's too many stinking colors.
It don't even matter. Here, whoa, plug that back in. What are you doing? Line it on.
You didn't check voltage to it or nothing. You don't even know if it got volts. It all should be energized, yeah.
You got power anything?
So no power.
So why is the condenser fan not coming on or blower motor?
Either one of them's coming on.
So where are you saying that coming for?
Well, hold on, I'm thinking. That's why. Fix that. See, there's too many staking colors.
Well, what's wrong?
I put this wire on neutral, so 120.
Oh, this getting scary now.
We're lean in.
I'm gonna have your arm over it.
There we go. Now all three of them running. So we got the compressor, condenser fan, and indoor blower motor. So now, just because we talked about this yesterday or last Tuesday, let's wire this, whatever this, what do we call this, indoor blower? Let's wire that in series with these three right here and see what happens. So if it's in series, what do we expect the voltage to do on these bulbs?
Divide evenly.
Divide.
So you wanna play that?
What you just do?
I'm doing series in parallel.
Oh, I did. That
Pressure's just got everyone watching.
You can watch what he's doing. Hang on,
It's
hang
all
on.
good, just wait it up.
We're gonna.
So you sure you got that on?
You guys.
We're gonna have to unwire this whole thing.
Hold on. You guys just hold on. They're plastic like that.
Got it. So why are the bulbs, why are they dim? Why are the bulbs dim? Exactly, so let's check the voltage. I can't remember which one I said. I think it was the middle one last time. We asked what the voltage would be. We go across it. We all think it's gonna be 80 volts?
Who's got $5?
Check it, let's see.
67. 40. Oh, now go across to 40.
Oh, yeah, it's gonna be 40.
Yeah, that's why I was asking. Sure, the other way was too.
So why is it 40?
Divided by 123.
Divided by 123 times, exactly. So what are the amps? What would the amps do? So we should know what the amps are, right? We know what the resistance is, and we know what the voltage are, so let's do the calculation. So what's the resistance? Volts or what resistance?
I think earlier it was like 25.
Right, it says 43 watts, but I don't see resistance. So if I said 25 or whatever, something like that, didn't I?
25 ohms.
Check it, but you got that one right there.
Yeah, check that one right there, Joe. I see what it is. So I was talking to Chris the other day and I completely didn't know what I was doing. So I was checking the contactor. I was ohming the contactor out and I knew what the voltage is, right? Because if I ohm a contactor coil, it tells me what the voltage is on the coil. So the voltage is 120, and I ohmed it like 2 ohms. So what would the answer be on that? 60? You think a contactor pulls 60 amps?
He's right. With the math, he's right.
Oh, I wanted to lie, my God, with an inch.
Can't do it on an inductive load. Contactor is an inductive load, right? What's the difference between a contactor and this? That's just resistive load, right? And inductive means we're inducing some type of voltage, current, or whatever, right? So we talked about how the contactor works. So how does it work? Someone tell me.
It's magnetic, creates a magnetic field.
Magnetic. So coil's energized, creates that magnetic field, pulls that iron in, right? So that's inductive. So we can't do Ohm's law on an inductive load. So because I was sitting there talking to Chris McKinley, I said, this ain't freaking right.
My unit was broke.
But
Ain't nothing wrong with this thing.
I totally forgot about it. Like I said, I've been out of the game for too long. You can't do it on an inductive load, just resistive. So like I said last time, Jared talked about, or asked me to talk about oil heaters on the train machine. A heat strip on your furnace or whatever, indoor unit. That's a resistive load, so you can do Ohm's law there. So if I know the amps, or if I know the resistance and the voltage, I should be able to know what the amps are on that heater before I ever put my clamp on it, right?
So a 700 watt heater at 120 volts, it's gonna pull how much?
Does everybody know how to convert watts? Know that chart, or know that?
700 watts, 120 volts.
5.83.
5.8. Should pull between 6.2 and 6.4.
You said 120.
700.
You said 700, 120.
700, 140.
So does every
So
wait?
what was the resistance?
No, you're
How
right.
much did I pull?
1.2 amps.
5.2 amps.
It's 1.2 amps.
Yep.
0.2 amps. Perfect.
You should pull right at 6 amps. If you did.
All right. Anybody got any questions on this? Pretty, like I said, you have to understand this. You have to be able to do this thing. Like, you should be able to wire this up. It's not going off this in your head. So if you got to sit down and draw it out, you sit down and draw it out. So sometimes it makes you more comfortable. I used to draw it out. If I didn't know it, if I didn't know how it really worked, if I didn't have a diagram or whatever, this is what I would do. I would draw it out and then kind of figure it out. Sometimes I drew it wrong, and then I just figure out what was going on. But again, you got to be able to know this to be able to do the larger stuff, because this is as simple as it gets. You go to an IntelliFact. I'm sure everybody's seen an IntelliFact for the most part. You're not going to see anything like this. It's going to be diagram after diagram after diagram. It's going to be electronics. It's going to have all those things. So if you can't do this, you're going to have a very difficult time doing an IntelliFact or any type of large unit. Even a like a precedent train package unit, 10 ton, 5 ton. They got a lot of electronic controls in them. I don't even know if they still have I don't even know what they have anymore. But I'm sure the top end or the higher end models have a lot of electronic controls or microprocessors in them. So doing away with a lot of the contactors and relays and stuff like that, it's all electronics now. So you got to be able to troubleshoot effectively. All right, you guys can have a seat. Dylan? You guys see our screen? See the PowerPoint?
Yes, sir.
You mix them all up?
That's messed up.
How many did you have?
Pick out the best one.
I had 5 each or so, 3 or so.
All right, guys, we're going to dive into motors. It's a little bit of controls. I mean, we talked about them a little bit. You see contactors. I got a couple of things up here. Like I said, I want us to be able to identify and start windings, run windings, and just kind of ohm out a motor and see what it does. And just a little bit of everything, I guess. I want you guys to make sure. I want to make sure that you guys have a good foundation, because like I said, I keep repeating myself, but if you do not have the foundation, you're not going to be able to get the job done like you want to get it done. Because I know everyone in here wants to be the best service tech they can possibly be. But if you don't put the work in, if you don't do the studying, if you don't do the reading, if you don't do the practicing or have whatever other word you want to call it or throw in there, you're not going to meet your potential. And that's just as simple as it is. So if you want to be the best, you're going to have to learn these things. So I promise you, I could ask multiple. When I say multiple, I could probably ask 100 people that interview with Oklahoma Chiller, and probably 5 would be able to draw that out. I'm pretty confident in saying that. I mean, it's not that difficult. They could probably figure it out. They could probably work through it. If they were on the job, they would eventually get there. But off the top of their head, they would not be able to draw that out. And I don't know how many people drew it out today correctly. You may have got close. You may have did it perfectly. I don't know. But you got to be able to do it. And again, hopefully this training will be able to do this and teach you guys, because we're here. That's what we're here for. We want to make sure that you guys are able to do those things that you want to do. So motor basics. Kind of tell me what you guys see in this picture that you can describe or that you can identify. So motor basics. What would you think a motor consists of? Rotor, stator, shaft,
Bearing,
winding. Windings is what?
stator,
Bearings, housing. What else is on there? And you basically listed all of them, but there's one thing that I see that you probably may not be paying attention to. Fan, exactly. So that's just the basic motor. So every motor is similar to this or whatever. I mean, maybe a little different configuration, but that's what it's going to look like. Does anyone know what kind of motor that is? When I say a motor, what type of motors are there? Anybody ever heard of a squirrel cage motor? Anybody know why it's referred to as a squirrel cage? Most AC motors are squirrel cage. Anybody know why it's referred to? Why they're referred to that? McKinley, you know why?
Squirrel, I would just say lower one, that's what I call them, squirrel cage.
I mean, similar to that, but that's not the reason on this. It's hard. This picture doesn't do it justice. It doesn't really show it. But if you had a motor or a rotor, which I didn't bring one in here,
Talking about open.
they'll have where the rotor bars are at. They'll have little lines in here. And those rotor bars, if you were to take them out, if you just see the lines, it looks like a squirrel cage. It looks like a squirrel cage motor if you were just looking at from the outside, looking at the flat end of it, or so to speak, however you want to say that, the wide end, I guess. So that's why they're called squirrel cage motors. There's 2 different types of rotors. This rotor is just a squirrel cage. There's another one that, like I said, these have bars. The picture doesn't do it justice, but rotor bars. The other one uses wire. So you'll see wire going through the rotor. You'll see wire just like it is in the stator, the stator. It's going through the rotor.
There you go.
I just sent you a picture, man. I don't know if I just.
You probably can't.
You thinking I've got too much technology experience over here, man. I've been messing this thing up. So again, squirrel cage motor. Someone tell me how a motor works. Just in general, how do you think a motor works?
Rotating magnetic field.
Rotating magnetic field, we talked about this a little bit Tuesday. So we say we put voltage to the stator, what happens? Chet said it creates a magnetic field, right? So it creates a magnetic field in the stator. Keep going, what happens? You guys know, just, if you don't know, just say something. What do you think?
Induction.
Induction? Induction happened, what does that mean? How does that motor turn? How does that rotor turn? It's not touching anything. So how does it turn?
The magnetic field induces.
Magnetic field. It creates a magnetic field in the stator. The stator creates a magnetic field. Starts turning the rotor, right? So as we start turning the rotor, start speeding up. Rotor creates a counter magnetic field. I don't know if anybody remember what we called that last time. Remember what I said about a wire? If you run voltage or current down a wire, a single wire, where it create that wire, that magnetic field can create a counter voltage. Anybody remember that? We'll talk about it a little bit more, but that's what we're doing. We're creating a magnetic field. Magnetic field starts turning that rotor. Rotor starts doing the same thing, because what did I say was in the rotor? Bars. Those bars are made out of what? Has anyone ever seen a rotor out? I know Jared has. What's a rotor look like?
Looks like a big chunk of iron.
Looks like a big chunk of iron. What do the rotor bars look like? I wish I had one in here. Do we have a rotor out there? Anybody know?
We did, unless Rudy might have threw it away.
Rotor bars are usually made out of aluminum. Because is aluminum a conductor?
Yes.
It is. Or are they made out of copper? So is copper a conductor? And just like the stator, the rotor is all intertwined as well. So you got caps on the rotor, and all those rotor bars and stuff are connected. So the rotor is basically another motor to a certain degree. So as we create electrical current or electrical current in the stator, it's magnetizing and creating another counter electrical current in the rotor. So if I got what attracts? Opposites attract, right? And so opposites attract. And
Would you like me to pull apart one of those motors for you?
no, that's fine. That's fine.
My mom.
So if we North Pole, South Pole attract, South Pole and North Pole do what? Repel. So just like I said, the stator is creating an electrical current, a magnetic force, and the rotor is creating an opposite electric force. So what it's doing is that stator starts turning, or as that stator starts turning when I say turn, it's not, the stator isn't turning. As we know, the stator is creating this magnetic force, but that magnetic force is turning, is going like this because we're energizing the coils at different times and such. So as this starts doing this, that rotor starts turning, and that rotor starts creating its own electromagnetic force. So they're working together to start this motor. Now the rotor is spinning, it gets up to speed, and that's as simple as I can say it. But that's what's going on. So just like, did anyone ever think of the rotor as being something that created its own magnetic force? I didn't have a clue about it. I didn't really look into it. But that's what's happening. So
are you saying like the stator's a North Pole magnet, and then the rotor's a North Pole?
exactly.
Right. So then they're pushing away from each other.
So as the magnetic force in the stator is getting the rotor spinning, is the rotor running at the same speed as that magnetic force in the stator? Is it faster or is it slower or same speed?
Lower
Slower. What do we call that?
slip.
Call that slip. Exactly. So if you got a motor or if you got a motor and you look at the nameplate and the stator is usually 3,600 RPM, is that motor or is that rotor actually turning 3,600 RPMs?
No.
It's not. Because where there's a little slip, there's a little distance between what the stator's doing and what the rotor's doing. So the rotor is always trying to catch up to the stator. And it never will. But they do have synchronous motors that are, we won't see them in our application, but synchronous motors, they run the same speed. So it's a little different. But that's what a motor is doing. So, my notes here. Dual voltage AC motors. So if we got dual voltage, how many coils do you think we have? How many windings do you think we have? 6? Definitely more than 2, right? Because the three-phase motor, just say the simplest three-phase motor, single voltage, how many windings you gonna have? 3. Anyone know how many watts is in the horsepower? Just a side bit of information.
746.
746, my man. So what would cause current in the motor to increase?
Voltage drops.
Voltage drop. What else? I'm not looking. This ain't any trick question. What causes motor current to increase?
Failing bearings.
Failing bearings. Why?
Drag.
Drag. What'd you say? Poor connections. Why?
Because it's struggling to make that connection electrically and heating up, which is causing more resistance to the
Exactly.
electrical flow.
What else? What are some other things? What about I'm giving you more ideas. What about a compressor? Why would it have more amps?
Excessive motor slip.
Excessive motor slip.
High load.
High load.
High pressure.
So I asked myself this question. I want to know what you guys think. I thought, well, Kristen, I asked him the other day. So everybody kind of understands the mechanical side of a motor. And I may be, and again, I want to preface it with this. I do not have a scientific explanation or a scientific reasoning or a scientific mind to understand this, to explain it intelligently. But I find this question amazing or fascinating. So a motor has 2 parts that are working. I mean, we got more than that, but the 2 main parts, the stator and the rotor, which are not touching one another, right? So the stator, rotor's inside the stator, and they're not touching. They have what they call an air gap. So there's a distance between the 2. Why do amps continue to go up when we only supply it the same, or when we supply the same amount of voltage? If that makes any sense. Why would amps, if I were to take a discharge valve and shut it on a compressor, my amps are going to do what? They're going to go up immediately. Why do they keep going up?
It's taking more force to turn that.
Resistance increase.
So I asked this same question to my instructors and couldn't get an answer. Really, I don't know.
Because
It has to do with the force. So the rotor is not, it's asynchronous. So now there's more slip. But why does it draw more current in the stator? I don't know.
yeah, because there's like I said, if I had a mechanical device or something, and I'm turning something physically or whatever, I can understand how it continues to go up or whatever. Or I got to put more force into the crescent wrench or the pipe wrench to turn this thing. But I'm not putting more force into it because I'm putting 460 volts to it still. If I had a pipe wrench and I put 20 pounds on it, I can turn it, and then it stops. So I put 40 pounds on it, doesn't turn. I can put 60 pounds on it, doesn't turn. I can put 80 pounds on it, doesn't turn. I can put as much as I want until I start breaking stuff, right? But a motor, I'm only putting 460 to it. So why do the amps continue to go up?
This is magnetic. So I guess if you're like trying to put it in a physical way, if you took two magnets and you held them further apart with both north poles, there's not as much pressure, but you put them closer together and it gets harder to push. So the magnetic field gets tighter and it gets harder to push the magnetic field away from the other.
Possibly. Like I said, am I going to tell you if that's a yes or no? I'm not going to, because I don't have that type of understanding of how electric works inside a motor. I got the basic understanding. So I know I'm kind of blowing your minds, but that's what I like. That's what I like to understand. Go ahead.
Put that in there when we talk about that again.
I just asked them. Yeah.
Back EMF and why it.
I haven't talked about that yet.
Are you going to?
Yeah. So when voltage is first applied to the winding of an induction motor, only the conductor. Listen to this. It kind of explains it. It says when voltage is first applied to the winding of an induction motor, only the conductor resistance opposes the flow of current. So what does that mean? Only the conductor resistance opposes the flow of current. What does that mean? What's the conductor resistance in a motor?
Motor winding.
Motor winding, exactly. Just the wire, basically, is the only resistance, right? So let's listen to this. Repeat that. When voltage is first applied to the winding of an induction motor, only the conductor resistance opposes the flow of current. So that's the only thing opposing it is the wire inside the stator. It's the only thing opposing it. It says because the conductor resistance is so low, so on a three-phase motor, what do we think the conductor resistance is? On a CVHE 1,000-ton chiller, what do you think the resistance is, Jared? If you were to ohm it out.
Say it's 100 ohms.
Not that much. Anybody know? I asked this last time. Chris?
2
ohms. It's going to be something like that. It's going to be pretty low. So it says because the conductor resistance is so low, the motor has very large inrush current. So what is inrush current? Just in simple terms, what is inrush current? Everybody knows what inrush current is. What is it?
Current on startup.
Current applied to the motor.
Locked rotor current.
Locked rotor current. So it's telling us that because the resistance is so low, when voltage is first applied, the resistance is so low, the inrush current is high, right? How high is it typically? What's the number? 7 times? I've usually low.
5 to 7.
5 to 7, 6. I usually say 6. So 6 times the full load amp. So full load amps is a 10. What should my inrush current be? 60, 50, 60, whatever number you want to use there. So 6 times. So it'd be 60 amps. So immediately I'm pulling 60 amps on this motor. And what's opposing current flow? What did it say?
Resistance of the
Motor
wire.
winding is the only thing because the rotor hasn't started turning yet. So we're pulling 60 amps, and the rotor isn't turning. It says, however, once the rotor begins turning, the rotor bars are increasingly cut by the stationary magnetic field. So what did I say? What did we talk about the magnetic field last Tuesday being cut? How does that work? If I got an electric field and I'm running a wire through it, what has to happen for voltage to be generated? We said the wire has to move in or out of that electric field, or the electric field has to move over that wire, right? So that's what it's talking about being cut. So by this rotor turning, what's it doing inside that magnetic field? It cuts it. So we got a magnetic field, we got rotor bars turning. So they're going in and out of that magnetic field, right? That makes sense? That makes sense?
Yeah.
Says, however, once the rotor bars begin turning, the rotor bars are increasingly cut by the stationary magnetic field, resulting in an increasing counter electromagnetic force. What do we say EMF was? EMS voltage, basically. Voltage, current, so it's got a counter, just like we said earlier. So the stator's producing a magnetic force, and now the rotor's doing what? Producing a counter magnetic force. That makes sense? This blowing everybody's mind? Way too complicated for a motor? So if we got a good understanding of this, so now we can start troubleshooting and doing things that most people don't know. Most people don't know this. And when I say most people don't know this, I didn't know this. So I had a basic understanding, but if we got a good understanding, like I've said 1,000 times, if we understand motor, how many times do we work on motors? Every day. We work on motors every day. I don't care if it's a 2 horsepower motor or a 1,000 horsepower motor. If you can become competent on troubleshooting motors, you just made a name for yourself. Because most people don't know how to do it, and they condemn motors when they don't need to be condemned, right? So, how many's ever condemned a motor that didn't need to be condemned? I have a bunch of times. Probably more times than I even know about, because I changed it out and I left and probably thought everything was good. It creates a magnetic force, counter magnetic force. So listen to this. If the rotor becomes jammed so that it cannot rotate, no more counter electromagnetic force is being produced in the motor winding. So no more counter electromotive force because that rotor stopped, right? So now there's no more force. There's no more counter force. It says this condition decreases conductor impedance. Impedance is basically resistance, total resistance, to the point that it is effectively a short circuit. So if we got a short circuit, what do amps do? They go up. So now the rotor stopped. It's at lock rotor amps, and we know this. We know, and if we put our amp clamp on it, that stator is going to be pulling high amps. So the rotor's not turning. It's pulling 6 times. What happens if we allow it to continue to do that?
Burn up.
Why? Why does it burn up?
From the heat from high current.
From the heat from high current. So let's look at it in another term or another application. What about a solenoid coil? Why do you have to put a stem or something on a solenoid coil?
Create a load.
Create a load on it, right? It's doing the same thing, right? So if I were to, again, I don't know the answer to this question. It's like Mr. What's the science guy's name? Bill Nye, the science guy question. Now, if I were to take that stator out, if I were to take the rotor out of the stator and I had the stator sitting here and I put power to it, what do you expect the amps to do on that stator? I'd expect them to be locked rotor from what we just heard, right?
Probably blow up,
Possibly.
like a solenoid coil.
Exactly. Let's try it. So when you're talking about these things, having a good understanding of it, again, like I said, it will help you troubleshoot it, help you know what's going on. It says alternating current flow in the conductor is limited by the conductor's resistance and self-induced voltage. Self-induced voltage acts to oppose the change in current flowing in the conductor. This property is called, I said this last week, I don't know if anybody wrote it down or not, because it's a term that I would recommend you learn for testing here, inductive reactance. So tell me what inductive reactance is once more. What does it do? You don't have to give me a scientific definition, but what does inductive reactance do? What we just talked about. It's basically a counter voltage creating more resistance, right? Counter EMF that creates more resistance. So just like it said for the rotor, what it's doing is creating a counter effect, giving more resistance to the stator, which in turn slows down what? Or limits what?
Current.
Limits current. So if I take that counter effect out, my current does what? Goes up. So I want to get back to the point of motors, and burning them up. So what happens to a motor when it gets too hot? We know it overheats or whatever, but what actually happens?
Windings short together.
Windings can short together, but what's separating the windings from shorting together right now?
Insulation.
Insulation, right? What type of insulation is it? Anybody know? Lacquer? Some type of lacquer? So that's all it is. So when when it gets overheated or whatever, that lacquer starts to break down. So then the windings can make contact with one another or whatever, create shorts or grounds or whatever you want to call it. So that goes to the next step. So we go out and again, we're not just talking about big motor. We can talk about this motor right here to do what we're talking about. Be an example of what we're talking about. So if this motor gets too hot, starts breaking down the lacquer, breaking down the insulation or whatever, how do we find that?
Mega ohm test.
Mega ohm test? So what does a mega ohm test do? Who said that? Somebody says, what's it do?
Test insulation.
How does it test the insulation?
See if there's a short, sends voltage.
Puts a voltage in the windings at a very minimal current, and you're testing for the leakage of that voltage, either to ground or between the windings.
Does everybody understand that? That's, 100% right. So how often do we do that?
Yearly.
Yearly? On annuals? So we do a mega ohm test. What do we do? How do we know? How do we record that?
Your annual log sheet.
Perfect answer. So, this goes back to being a technician. We do record our annual log sheet, but let's say I did the annual in 2022. I did a mega ohm test on this motor here. I go back in 2023, I did another mega ohm test. What does that tell me?
If those windings have degraded over that time span.
If they have degraded. So what would we expect a mega ohm test on a brand new motor to be?
2.2.
2.2. What does that mean?
Giga ohms. That means it took 2.2 giga ohms at 1,000 volts. No continuity to ground or between windings.
That means basically, like you said, that basically 2.2 is basically like we looked at on our meter and said, OL, infinity. So there's nothing going between the windings and the casing, the motor housing or whatever, or between the windings. So that insulation is perfectly, for lack of a better term, sealed. But my point, what I want to get to is we record that or we write that stuff down on a log sheet, but how many people look at it when they go back the next year when they do it again? So if I had 2.2, basically no path or insulation is perfect, and then I go back in 2023 or this year, and I've got 100 mega ohms. So did my reading go up or did it go down, or say get better or get worse? It got worse. So how do I know that? When I say I know it right now, but how do I know that compared to last year?
Write it on a panel or something, right on the motor.
Do you look at your log sheet every year?
Write it somewhere, you have to see it.
You can do that, but if you have, that kind of tells me, and no offense, kind of tells me you never logged it or made the motor before.
I've never had no.
Because why? Because there's a lot of numbers involved in that, isn't there? There's a lot of numbers if you want to write this down. So basically the point is we got to do a mega ohm test right, you got to trend it. Unless it's just absolutely bad. You know what I mean? If I go up there and I make this motor that makes 1 mega ohm, I know the motor's bad. If it's blowing breakers or whatever, I know the motor's bad. Or if it's still running, which is highly unlikely but possible, I know the motor's about to go bad. But if you don't trend it, it doesn't really do you any good. Because the opposite end of the spectrum, yeah, you can figure that out quickly. But if it goes down slowly, it doesn't do you any good unless you know what it was last year, the last time you megged it. That makes sense? So that's another thing as far as a technician, you got to be able to do those things. You got to be able to keep that log or be able to reference it or be able to get to it somehow, some way. Dylan, I know Dylan's had this issue at Chesapeake, because I remember him talking about it. Dylan, what do you do to be able to reference your past Meg-Ohm tests?
I keep all the log sheets. They're in a little book inside the unit, but if that gets lost, I can always reference it on XOI. And I have all the Meg test readings written on the paper log sheet.
So at Chesapeake, they record basically everything they do on these machines. So they're really high on maintenance. So everything we do, Dylan does, whoever's out there, they write it down, and they put it in their folder. So if we have a contract, that's something we could do, but you got to be able to get to it. You got to be able to reference it. So going back to it, you're actually going to the testing. How do you actually Meg-Ohm, or how do you Meg test the motor? If I want to put my meter on here and test the motor, how do I do it?
On a 6-lead motor, you're going to test it 21 times. Because you're going to go from terminal 1 to ground, 2 to ground, 3 to ground. You're going to test them all to ground, and then you're going to test them to each winding. 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 2 to 3, 2 to 4, 2 to 5, 2 to 6, and so on until you get them all tested. And you'll actually test the motor twice. Because when you're testing them lead to lead, you're going to test 1 to 3, then you're going to turn around and you're going to test 3 to the other winding. So
you basically just go down, start with 1, and start working your way down the line. So again, I didn't get a number of hands or number of people. How many have not Meg tested a motor before? Okay, so a few of you. So when you Meg test a motor, I should have brought my Megger here. I do have my Megger. And we'll do that here in a second. So you basically push a button. It's just, it's a simple meter. So I put my leads to the motor, to the windings, or to the leads, motor leads. Put my leads, or my meter, I can't even talk. Put my meter on Meg-Ohm test. Like Jared said, this one does 50 to 1,000 volts. I always test at 1,000 volts. So do that, and then once everything's set up, you just push this button. So once I push this button, it puts 1,000 volts to that motor, DC. So someone come up here, hold these 2 leads, and let's check it out real quick and see what happens. See what it feels like. But anyways, as I push that button, it can
hold on just a second. So when you're Meg tested motors, the rule that I've always been told is if it's a 460 volt motor, you test it at 1,000. If it's 120, you would test it at 250. If you tested it twice, it's rated voltage. So if I have a medium voltage 4160 motor, I've got to take it to 10,000 volts. That makes sense?
And I don't have a 10,000 volt Megger. You do too. Yeah, we do. So yeah, that's a good point. Because if the more voltage you put to it, the more capable. If you were to put 10,000 volts to this motor, what do you think it's going to do? It's going to burn it up, right? You're going to create leakage. You're going to create windings damage and stuff like that. So I push this button. As long as I'm pushing that button, it's giving voltage. So if to those that have Meg the motor, I push this button. What happens the longer that I hold the button down? What happens to the reading?
Going up.
Goes up. So is there something to that? Again, I'm not asking the question right. So say Ethan makes a motor and he holds the button for 1 minute and takes the reading. I make a motor and I hold the button for 15 seconds and take the reading. Are we going to get 2 different readings?
Yes.
Exactly.
So make note of that on your log, right?
You can make note of it, or you can all do it the same, or however you want to do it. So that's one thing too. So if I hold this for 15 seconds, take a reading, I may get 100 megs. Ethan holds it for a minute, he may get 700, 800, 900 megs.
Why is that? Is that because of pulling the off the battery on the meter?
Why is that? I don't know.
to be honest with you.
I got a question on the mag, because so like you're talking, like we get the high number, right? So you might get 150, 200, whatever. So why is it that a bad motor is generally 1 or 2 megs? But like, I've never seen like 5, 6. Like it's generally like one end or the other.
Well, I've seen them like that, but I mean, I don't know how to answer your question, because I've seen it do that. I've seen, I mean, in particular, I remember, the specific moment. Was megging a motor, it was on a train in Telepac, and it would pull 4 meg on, or it was megging 4 meg ohms, but it was still running. Why would that motor meg 4 meg ohms still be running?
The windings haven't touched yet.
Windings haven't touched yet. What else? What can cause it? It was a blower motor. Why would a blower motor be doing that?
Moisture in it.
Moisture, exactly. So it's got wet. So those types of things can give you I wouldn't say a false reading, but a low reading. So if we were to let it dry out or whatever, turn the blower motor off or get it out of there, that meg reading would go up.
So I have megged what is it, RTHB screw chiller at the top of Dollar Thrifty Tower. And I was supposed to put terminals in it, take the end bell off of it, and replace the terminals. And I megged that thing before I took the gas out of it. And it would take less than 1,000 volts. It was like 800 and some volts. And I thought, this thing is shorted. Took all the gas out of it, perfect. Make it perfect. Put the gas back in it, same thing. Fired it up, ran.
There's one in the city like that too. It's making, I think 7 meg ohms of ground.
Why was that?
Like 2 or 3 other companies shot it down.
So another I wouldn't say example, but it's just another thing to think about. Can you meg a motor in a deep vacuum?
Not supposed to.
Why?
Behaves differently in a vacuum.
So exactly, we never meg a motor in a deep vacuum. By deep vacuum, there's a train centrifugal in a vacuum. It's in a vacuum, but it has refrigerant and such, but it's not a deep vacuum. So if you're ever pulling if you're evacuating a chiller and you got it down to 30 inches, and again, everybody knows I'm just saying this, we don't get it down to 30 inches, but you know what I mean. And you meg a motor, there's a possibility you can damage the motor. So don't ever do that. Let's be mindful of those things. And same thing with a VFD. Do you meg a motor with a VFD still attached? Why?
You blow up the gates in it.
Have you ever, I've done this, have you ever hooked up a VFD backwards? And it's not I wouldn't say it's not fun. Marshall and I were on VOK, I don't know what they call it, VOK Tech Center, I think is what they call it. And it was dark, it was at night, we got a late call, VFD wouldn't run, blower or indoor fans wouldn't run, so we had to change out the VFD with the VFD that was on the exhaust fan. I don't know if you guys ever worked on them. Took the VFD off the exhaust fan to put it on the indoor blower motor. And again, like I said, it was dark. We hooked the wires up, thought we were good, turned the power on, boom, blew up. One of the loudest things I ever heard, really, because I was just right there inside the panel. And learned that the hard way. So do not, if you got a mega motor, you disconnect the VFD, disconnect the solid state starter. And what else? I know
Well, there's a bypass contactor, an isolation contactor on the VFD when you throw a bypass on.
What'd you say?
So that's why there's an isolation
Oh.
contactor underneath the VFD when it has a bypass.
And the centrifugal guys may know this. I don't think they do this on any other power factor capacitors. Has anyone ever tried to make a motor with power factor capacitors? What does it do?
It reads shorted.
Reads short. It reads bad, right? You're like, Dad, gum, I got a freaking motor bad. But it's not. You got to disconnect those things again. So
Let me tell you how embarrassing that is when you mess that up. When you do it the first time, you already tell the customer, then you call Faber. It ain't freaking shorted. It's got power factor capacitors. I don't know, what's that?
Exactly. So those are things you got to watch out for. And again, just understanding what you're doing. And
making sure that you isolate. It's just like checking a compressor or a motor. Compressor is probably the best example for me. Condemning a compressor at the contactor. That's what that's like, because you didn't go right to the motor. You didn't go right to the motor leads. And I tell you, I've condemned a compressor from the contactor before. That will make you feel stupid. So kind of going over motors, split phase motor. Can someone tell me what a split phase motor is? What kind of motor is this right here? Single phase. It's got 3 leads. What is that?
DSC.
DSE. Split phase. Capacitor. What's a capacitor start motor? They're basically all the same motor, but a little difference. Capacitor start. What does that mean? Capacitor start.
Has a start
That's a
capacitor.
start capacitor. So what type of motor would have a start capacitor? What application?
Compressor.
Compressor. Capacitor start, capacitor run, permanent split capacitor motors, 3-phase motors, all pretty much the same motor except for the 3-phase motor, right? I mean, what do we see the most of? What type of motor do we see most in our application, in air conditioning? We're going to see this. This is what type, what would this be for? An interfan. 3-phase, we're going to see on everything for the most part. And blower motor would be what type of motor? ESC. Does the blower motor ever have a start capacitor?
It has a capacitor run.
Capacitor run. Just like the condenser fan, somebody asked a question earlier or answered it. Why do we not need a start capacitor on a blower motor?
We don't have a high load or a
No.
high starting.
Doesn't need much starting torque. So, 3-phase motors. Why does a 3-phase motor have more torque than a single-phase motor? Anybody?
Because you're getting 3, your sine waves are 120 degrees out of phase, so it's getting pulsed more often in the same period of time as split phase.
Damn, Chet. Man. You're like an electrical genius, dude. So right here is the sine waves for a 3-phase power. So if I had single phase, what would I do? Take away 2 of those, right? So at this point right here, how much voltage do I have?
0.
0 volts. So as I go up, let's look at the black phase. I guess it's black. I can't tell. Purple. I think it's black. So if I go up to the 1.0, how many volts would I have? It's 460.
70.
How much? I go all the way up right here at that 90-degree angle. So it would be 460. So to get to here, how much volts did I got on this one? What I got here? 0. So if I look at these angles, I go here, phase 1, I got full voltage. If I go down here, I got full voltage. So if I were just to have single phase, you can kind of see how they cross. So we constantly have power. Does that make sense? We constantly have power. And like we talked about earlier, I didn't mention this. But as we go up, what do you think that magnetic field does when I get to the peak on anything? The magnetic field going to be high, low?
High.
It's going to be high. What do you think that magnetic field does when it get here?
Switches.
It goes to what? So high, low, 0?
0.
It goes 0. So when I get down here, what does it do?
Peaks.
Peaks again. So I built that magnetic field. So that magnetic field doing this. So I think I talked to Chris about this. I'm pretty sure I did. So I got this contactor out here for a reason. Has anyone, I won't take it apart right now, but has anyone ever took the coil, looked at the coil and it has a little clips on it, on the coil? What happens when those clips are gone? Buzzes. Vibrates. It does. It makes a loud noise, right? You know what that's doing? I just learned this other day because I didn't know what those clips are for. I knew they had to be in there because, like you said, it buzzes, doesn't work, sounds like crap, feels like something's about to fall apart. So what that is that's called a shading ring. So again, let's pretend we got two of these gone. We just got one phase now. So just like I said, so as that phase gets here, what's that magnetic field do? Goes in basically nothing. That magnetic field is building, collapsing the whole time. So those shading rings produce another magnetic field that is not, I think it's 90 degrees out from the sine wave or whatever. So it's like you see here, these are 120. That shading would be, I think, was like 90 if I'm correct. Don't hold me to that, but I'm pretty sure that's what it was. So when that voltage or that sine wave gets to there, where there's no magnetic field, that shading ring produces or has a magnetic field. What do you think it does to that coil? Where do you think that noise is coming from without the shading rings? If that magnetic field is going away. You said it takes a magnetic field for it to pull that coil in, right? Pull that iron in. So if that magnetic field is going away for, I mean, a split second, I mean, I don't know what the time is, but it's small. So it does what?
Lets out.
Lets out. So that's what, when it lets out, it's backing off. So that's doing this. So when that field builds back up, pulls in. Goes away, lets out. Builds up, pulls in. Goes away, lets out. So that's what you're hearing. You're hearing that thing just set there just a little bit, real fast. So if that coil is backing out, what's the contacts doing? Backing off. They're backing off too. So if the contacts are backing off like this, what's it doing to the contact and what's it doing to the motor?
Making lots of little nice sparks in there.
Exactly. So a contactor like this, can you replace contacts on these?
Yes.
Are contacts cheap? They're not. So if we were allowed it to happen, to continue to happen, contacts will pit. So if we give enough pitting in the contacts, what's going to happen to the stator, the motor? It's going to cause excessive current or more current, somewhat, or whatever it may be. We may weld the contactor. I don't know. So that's what those clips are for. So make sure those clips are in there. If those clips fall out, you got to put them back in to get the machine running or whatever, how critical it is. But do not leave those clips out and walk away from the job. How many's ever left the clips out and walked away from the job? I have, because I didn't know what they were. But that's what it's doing. By studying for this class, I learned that. That's what I'm talking about for you guys. You guys got to learn that stuff as well. And that's what I'm trying to teach you. So whatever I don't teach you, you got to learn on your own. Whatever Chris doesn't teach you, you got to learn on your own. Whatever you don't teach yourself or others teach you, you got to learn on your own. I've been doing this since 2001, so 22 years. And I just now learned that. So, and not to be braggadocious, but I consider myself pretty good. And I just now learned that. I should have learned that a long time ago, but I didn't.
I didn't know you could glue those clips back on.
Well, I don't know how effective it is because I think Chris was talking about it. We've done it. I've done it. It's never the same as replacing iron.
I think it's the epoxy is what I think. I think
He's always epoxy.
conductive epoxy. What you use, Gorilla Glue, not it. That's not what you use.
Gorilla Glue does
It
not
was
work.
quieter, but it didn't last long. I think the iron burned it up.
What if you use some like an Aegis epoxy, like Aegis grounding rings, the epoxy? Well, we can buy the iron for those from a company called Anchor Electric, and it's way cheaper than Train.
So stupid question, simple question. Do you need starting components for a three-phase motor? Anybody ever seen a start capacitor on three-phase motor? No, you don't need it, won't see it. Just because, like I said, we got power applied to it at all times. So the book gave an example of a 3-cylinder engine compared to a single-cylinder engine. So just like on a 4-stroke engine, how many times do you actually compress? Once out of 4. You got 4 strokes in there, so 3 of those strokes are basically useless, right? I mean, they're not generating any power. So that's kind of the same thing. If you had 3 cylinders, at least 1 cylinder is producing power at all times. That's what we're doing here. Oh, dual voltage, 3-phase wiring. I don't know if y'all, I'm going to bring this out so somebody don't say something. Is that right? Is that wrong? Wrong. So, I'm trying to think of the, everybody's seen Tombstone? Doc Holliday says, "I'm your Huckleberry." And everybody wants to say, that ain't right. That's supposed to be, "I'm your Huckleberry." Somebody always got to say that. Every time. It's on my nerves too, man. So I pointed it out for somebody to say it. So this is a dual voltage motor, 3-phase motor. So does everybody know how to wire up a dual voltage 3-phase motor? Or who has wired a dual voltage 3-phase motor? Everybody, for the most part. So you know these numbers, right? The wires, the leads are always numbered. So just like we did on the light bulbs here, what happens when we put the voltage through these coils? What's the voltage do? Those coils. It's going to divide, right? So over here, what's it going to do in parallel? It's going to stay the same. So you see what we're saying? So here, they're in series. Here, they're parallel. Here, in parallel, is 230 volt. Here, in series, is 460 volt. So each wire basically begin half the voltage, right? So we're doing the same thing, we just configured it differently for whatever voltage is supplied to the motor. So how many windings do we have there? This is a simple question. 6 windings. So we got 1, 2, 3, 4, 5, 6. These 3 right here are tied together internally. All these others is what your leads would be. So if I were to put 460 or wired up for 460 or wired in parallel for 460, what's going to happen? You're going to burn this motor up real quick. But if I wire it this way, but I have 230, what's going to happen? Not going to cause any damage. Just won't have any power or anything like that. Just like those light bulbs, you won't just be running, like Jared said, it won't be running right. Do not. How many ever have used the, I don't know if we still have the hot water machine.
Yes, we have that. We still have it.
How many's wired it wrong or hooked it up wrong? So those are the types of things you gotta be looking for. Basic motor, motor basics here, man. Here it is, the diagram. So if you were to wire it up, this is what you'd get. You just wire those leads up just like it says there. Pretty simple. But it gives you an idea of what you're doing. That's what you're doing by wiring it up. You're wiring it up for low voltage, it's gonna be parallel. For high voltage, it's gonna be what? Series. Motor controls, just relays. Where do we use a relay? What is a relay? What is it? Says open and close contact. Open and close contact. Where would we use a relay? Most common place to use a relay. fan, indoor fan, right? So indoor fan, low amperage, light duty stuff. So can you rebuild the relay? You know, you're just gonna replace it. Simple, I mean, very simple stuff. Contactors, definitely rebuildable. So if we were to replace this contactor right here, what do you think that thing costs? Thousands? Probably $5,000 to $10,000 to replace this contactor. So these things are rebuildable. Maintenance, you want to do maintenance on these every year. You want to pull them apart, but one of the most high priority things on it is what we said earlier. What do you want to make sure is good and clean and good, in good shape? Contacts. So what do you clean contacts with?
Dollar bills.
That's right. What'd you say?
Dollar bills.
Dollar bills. Somebody said that the other day. I don't know who said. Oh, no, they're talking about cleaning the flame sensors.
King said dollar bills. He said if you're rich, you can use $100 bills.
So contacts, auxiliaries. Well, what's the auxiliary do on this contact? What do they do for the most part? Auxiliaries usually mounted on the side for what reason? What do they do? Anyone?
To be run proof.
Exactly. Just got some type of status or something like that. So if I have an auxiliary go bad, and I've done this in the past, the only reason I bring it up, what can you do to replace an auxiliary if you don't have an auxiliary? Contactor? How? Relay? How? How would you do it? How would you wire it up?
Parallel control voltage.
Parallel to the coil, right? Because all that auxiliary is doing is telling whatever that this thing is pulling in. So if you got a contactor, a small relay, it would do the same thing. You wire it parallel to the coil, so this contactor pulls in, it's going to pull in that relay / contactor, and it's going to give a signal or a status to whatever it may be. So those are the types of things, again, you learn over the years, and that will get you out of a bad spot, tough spot. But do you want to leave it that way? Don't leave it that way. Fix it, or go back and fix it the right way. So thermal overload or starters. What's a starter? When I say a starter, what does a starter usually have, or it has to have, really? Overload, contactor, overload. So how does this work? How does this sense current and open up or whatever? Heat, exactly right. So the more current, the more what? More heat. So pretty simple. Everyone's, I'm assuming, has messed with these, seen some type of device like this. It's got a setting on there to adjust the heat rating. So once it hits that heat rating, it's going to trip, recycle or whatever. So basically, these would be mounted in the bottom of the contactor. Then you'd have your wires going to your motor or whatever coming out the bottom of this. So pretty simple, but the main thing is to protect the what? Motor. Thermal overload. What's a thermal overload? What does it do? Temperature rise. Capacitor. Everybody knows what a capacitor does. What does a start capacitor do?
Starting point.
Starting torque. What's a run capacitor do?
Provides efficiency.
Provides efficiency for what? What does it do though? Just in general terms.
Fix the run winding. Start winding.
Start winding. Allows the start winding to stay in the circuit, right? Dylan or Hank, if y'all still there, these guys know how to do this. I didn't know how to do this. I still don't know how to do it. How do you check a run or a capacitor while the machine's running, while the motor's running?
All right. Hank's gonna take this one. I can't remember the bottom number. It's 1375, 1175.
I don't know. Thankful.
1 second. 1 second.
Did you know that you can check a run capacitor while it's running?
We used to
It's
have
actually
papers
supposed to be more accurate.
up there at the counter that told you how to do it.
I don't think Hank and Dylan know how to do it.
I actually have it
Yeah,
on
we
my
do.
phone.
I was looking through my old papers, so give me a second.
It's your voltage across your capacitor. Hank's looking it up, but I'm gonna take a crack at it. Take your voltage across your capacitor, multiply it by your amperage, and you divide it by a constant, and I can't remember. It's a 4-digit number. I can't remember what it is. It's
2650.
2650. I'm pretty positive.
So put that, if you don't mind, put that in the Teams group, so everybody can have that. So again, I didn't know, I mean, my experience has been mostly 3-phase stuff. So you do a lot of the single phase work on condenser fan motors or whatever it may be, you may want to use this. Maybe it may come in handy. But how does everybody else check?
Ground the capacitor first.
Yes. You just check it with your meter, right? Just check it with the capacitance on your meter for the most part. Transformers. I just threw this in there because, again, I just kind of found this kind of interesting. Transformer winding connected to the voltage source is called the primary. Transformer winding connected to the load is called the what? Load side is the secondary. Transformers can be used to either raise or lower the voltage. Is there a difference between a step up and step down transformer as far as how it's built or whatever?
Yes.
There is. You sure?
100%.
What's the difference?
So the difference is if you backfeed one, so if you think of you're using to drop the voltage, something like this, all your current is going to be hit on like the low voltage side of it. If you reverse feed it, they increase the winding size on the opposite side of the transformer. So it's made to where the secondary side can now take the inrush current.
I did not know that. I knew Chris had told me that you could, or that there was a difference, but I didn't know there was a difference.
I didn't know that either. I found out when we bought some for the rental fleet, and I said, "Can we reverse feed them?" And they said, "No." I said, "Why not?" They said, "We're not made to be reverse fed." And I asked them what the difference was, and that was it. Basically, what they'll do is take the primary side and they'll increase the winding size on it versus doing it on the secondary like a normal.
The voltage level that can be induced in the secondary winding from the primary magnetic field is a function of the number of secondary conductor loops that are cut by the primary electromagnetic field. I'll read this. I found this interesting. Again, it kind of goes back to conductive reactance and stuff. It says the following steps explain the process of primary and secondary flow in a transformer. Step 1, when a load is connected to the secondary of a transformer, secondary voltage induced from the primary magnetic field causes current to flow through the secondary conductor winding. Wiring. So that's pretty simple there. The secondary current flow in the secondary winding creates an electromagnetic field that opposes the primary electromagnetic field. So again, we're opposing. Secondary is opposing the primary. Just like we talked about in the motor. So the flux lines, what are the flux lines? Just another term for something else, something simple. Magnetic field, remember those lines we drew out? That's basically the flux line. So we got a magnet here, and we had some metal. The closer we get to that magnet, the more it's going to have a pull towards it. That's the flux line. So the farther away, those lines don't have much power, but the closer we get, those lines have power. So again, how do we create voltage? What has to happen? Something has to move, either the wire cutting through the field or the field cutting through the wire. It says the flux lines from the secondary magnetic field effectively reduce the strength of the primary flux lines, and as a result, less counter EMF is generated in the primary wiring conductor. Wrong button, gentlemen. Man, I messed that up a little. It says with less CEMF to oppose a primary voltage, the primary current increases in direct proportion to the secondary current. That doesn't make much sense to me there. Says county electromotive force is known as back electromotive force. The electromotive force or voltage that opposes the change in current which is induced. CMF is EMF caused by magnetic induction. I know that probably doesn't mean much to anybody. Auto transformer. Can anybody tell me how an auto transformer works? Or what it is? What's the difference between an auto transformer and a regular transformer, primary, secondary transformer? Anyone? Another thing I didn't know the difference. Auto transformer only has one coil. So it doesn't have a primary or secondary. It uses one coil to do the primary and secondary. Just taps it in different spots. I should have put a picture of that on here, but I didn't. It says auto transformers use a common winding for both the primary and secondary, and their purpose is to step up the voltage, step up or step down the voltage. Secondary winding of a step down transformer has fewer turns than the primary winding. We know that. There's another thing I thought was interesting. Who knows what an eddy current test is? So these transformers are producing eddy currents. Anytime there's really a magnetic field, there's eddy currents. So I didn't know that. So the eddy currents are looped current, electric current induced within conductor by changing magnetic field in the conductor or by the relative motion of a conductor in a magnetic field. There's a lot of magnetic in there. Circulating eddy currents cause the iron core to heat up without any useful purpose. So just like I got the picture of the transformer here, that's what it's doing. It's heating up that core. To reduce losses because of eddy currents, long laminated iron cores separated by insulation, usually lacquer, are used. So that's why your transformer has those sheets and they're coated with lacquer. Did anyone know that was the purpose? Because you're producing the eddy currents in here. And it causes heat to build up and current. So if I were to take this lacquer off, and again, I don't know the answer to this question, Bill Nye, the science guy question. If I were to take this lacquer off, would this shock me? Probably. Let's try it. They burn you. You'll get a torch. So again, just another tidbit of information to kind of understand electrical stuff. So again, we can talk about the simple thing. When I say simple, the everyday things, because you're not going to use it. This doesn't really affect your everyday use, but it helps your knowledge of understand better, have a better understanding of it. Just like this right here, three wires. So this would be my windings, right? What do you think these two wires are for? This is a 3-phase motor. Why does it have 5 wires? Somebody said something. Thermal. I don't know that's what it is, but that's a pretty good guess. So if you guys that don't have much experience with wiring a motor, and you saw this is a 3-phase motor, everybody knows 3-phase motors have how many wires? 3 leads. So you go up to this, you see 5, what are you going to think? What are you going to do? So knowing, what'd you say?
Look at the diagram.
Look at the diagram. So just having that knowledge, most people may call somebody and just kind of ask somebody else to help them or do it. But if you have good understanding, you don't have to have those things. You don't have to do those things. The only time you're going to need help is when you really need it. And I promise you guys, the more you think, the better you're going to be. Because a lot of people, and I've been guilty of this. Get on something I'm not familiar with, and the first thing I do is make a phone call instead of trying to figure it out. So try to figure things out. Use your brain. Think about these things and how they work. And then if you need help, there's no problem in calling somebody. But the main thing is you got to be able to think on your own, because I know this is generic. Everybody hears it, whatever. That's what you get paid for. It is. And if you can think, I promise you'll get paid more. I promise you that. So this is what these classes are for, to teach you how to think, really, in my opinion, because this information, I heard this the other day, and it's so true. Do you even need to go to college? If you were a thinker and you were self-sufficient, do you even need to go to college? I can find out anything I want to on YouTube, the internet. I mean, I can find out lots of stuff. if you're willing to put the time in. I'm not saying that college isn't good, because it puts you in the right direction or in the right path or whatever you want to do. But man, if you can think you're going to be invaluable, if you can do things that no one else will do, that's what's going to separate you. Coming to these classes, that's what's going to separate you. I told Hank this earlier, and he asked me a question about last class, and I can't remember exactly what he said. Basically, how the class go or something like that. I said, well, it went good. I said, and this is the way I think. This is the way I am. I know people make fun of me for it, but I said, if you want to learn, you'll learn. I don't care if the dumbest person in the world's up here talking. If you want to learn, you'll find a way to learn. And but again, I had to put in the research. I had to do my part as well, because if I don't do my part, I make your learning harder. Does that make sense? And that's what we got to do as a team. If we can do each do our own part in learning, building each other up, these classes, and not looking for someone specifically to basically spoon feed you information. But if you're hungry for information, people will be way more helpful to you. They'll give you things because they see your hunger. They see that fire. They see that hunger that you have. But if you're not hungry, if you're not willing to put the work in, or not willing to study, not willing to think, most people won't help you. I mean, they'll help you, but they'll put the same amount of effort you put into it. Does everybody agree with that? Mm-hmm. See, like McKinley, like I'm trying to teach this old boy something, but he don't learn nothing, man. All right, that's all I have for tonight, guys. I think it's about time anyway. Anybody got any questions?
From earlier about capacitors.
Yep.
So I have learned and been told and understood that you always try to discharge a capacitor because it could hold a force and get you if you're not careful. So to this day, I have not come across one that was. Does anybody know why it would or would not have a charge still on it? I do not.
Enough time to drain it.
So a run capacitor will not have a charge. So if you're doing one that's metal, it doesn't hold a charge. A star capacitor will hold a charge, and the reason why is because the voltage is so much higher, it takes a lot longer to dissipate. So
They usually have bleed resistors on them.
yeah, if you look on there, they'll have a little resistor across the tube. But next time you see a star capacitor, just start the motor, turn it off, and touch it.
Before the blade. Be sure you set your phone up and video that too.
Appreciate it, guys.